Hi, I'm Herb Gross, and welcome to Lecture 19 in Gateways to Algebra, where today we're going to look at a very special function. There are other special functions that we could look at throughout algebra, but this particular one is one that's very important, and also it's dramatically different enough from a linear function so that we begin to see quite a contrast. But by way of review, let's start with looking at a linear function again. And let's simplify it by just having the b part be 0. Suppose f of x equals 2x, which basically says what? Whatever the input is, the output will be twice the input. So f of x is 2x. Let's do something we haven't done before. Instead of putting a number in here, let's put an algebraic expression in here. Let's replace x by x plus 1. By the way, before we look at that, what that's telling us is, given that this is the program, that this is the rule, the recipe, what this says is, what happens to the output when when the input is replaced by one more? See, whatever x stands for, x plus 1 means 1 more than x. Now what does this rule do? Whatever the input is, it doubles that. So whatever you put in here, you also have to put in here. So if I replace the parentheses by x plus 1 over here, I also have to put x plus 1 in parentheses over here. By the distributive property, when I multiply x plus 1 by 2, I wind up with what? The 2 times x is 2x, and the 2 times 1 is 2. So f of x plus 1 is 2x plus 2. Now what did 2x stand for? 2x was f of x. So replacing 2x by f of x, look at what this thing says. This says when you, see, the input is what you're putting inside the parentheses. The output is what you get out, in other words, when you're all through. What this says is if you increase the input by 1, what happens to the output? It increased by 2. In other words, and by the way, x could have been any number here. So what this says is no matter what x is, every time x increases by 1, f of x is going to increase by 2. So let's just start at a fairly simple place over here. Let's just start at 0, 0. Now this says what? Every time x increases by 1, y is going to increase by 2 in terms of the graph, right? Every time the input increases by 1, the output's going to increase by 2. So what do we get over here? 1 over 2 up, 1 over 2 up, 1 over 2 up, 1 over 2 up. And we get this staircase effect. In other words, what we wind up with, if I've done this thing right, should be a bunch of points, all of which lie on the same straight line. By the way, I should make a disclaimer here. Somebody came in who was watching the monitor from outside and thought I was bleeding. If your monitor is clear enough so that you can see these red marks on my fingers, it's not from the director beating me or from my being cut up. It's the red marker from the pen that I'm using. So thank you for all your sympathy, but I'm not hurt. Okay? Let's go back to work now. Okay. Now, you see what happens over here? Let's read what this says. This is the form y equals mx plus b, where b is 0. That means that this cuts the x-axis where the x and y-axis meet, and it goes up, what, 2 units for every one you go to the right. And this is now a rather gradual, at least it's a steady rise. In other words, the slope is constant. Now suppose instead of writing 2x, this may not look like much of a difference, but instead of writing 2x, suppose we just put the x a little bit above the 2, which now makes this 2 to the x power. See, f of x is 2 to the x power. Let's take a look and see what that says. This says, what? Whatever the input is, the output will be what? 2 raised to that power. So for example, if the input was 3, the output would be 2 to the 3rd power, which is 8. But suppose the input was x plus 1. If I put x plus 1 in here, I also have to put x plus 1 in here. So f of x plus 1 is 2 to the x plus 1 power. Now we have to remember our rules for exponents. See, when you have the sum as an exponent, that means that was a product. In other words, how do I wind up with x plus 1 as the exponent? See, 2 to the x times 2 to the 1. This is why all these rules were important. Do you remember what the rules were for multiplying like bases? You kept the common base and you added the exponent. See the trick? Adding 1 over here is the same as doing what? Multiplying by 2. So look what happens over here. F of x plus 1 can be written as 2 to the x times 2 to the 1. Now 2 to the 1 is just 2. What is 2 to the x? 2 to the x is f of x. So what this says is something very interesting. What this says is when you increase the input by 1, look what happens to the output. You don't, the same 2 is over here, but you're not adding it. What are you doing now? You're multiplying by 2. In other words, now if x increases by 1, f of x doesn't increase by 2, it does what? It gets multiplied by 2. In other words, it's doubled. Now, watch what dramatic effect that has. See, first of all, remember that we've always defined 2 to the 0 to be 1 in our earlier lecture. So when x, let's graph y equals 2 to the x. See, when x is 0, y is 1. Now, that's your y value. What's going to happen every time x increases by 1? The y value is going to double. That means that the height of this column will be double the one that came before. So if this is 1 unit high, this is going to be what? 2 units high. Well, so far, nothing dramatic. But now what happens? We're going to increase x by 1 again. Now remember, every time x increases by 1, the output is going to double. So if we increase the input by 1 here, the output was 2. Now what's the output? 4, because double 2 is 4. Now we increase by 1 more. We increase by 1, the output is going to double. The output was 4. Now what's the output? It's 8. Well, look what happens. Look at the actual change in the height of the column. This went from 1 to 2, so it only increased by 1. This went from a height of 2 to a height of 4. That's an increase of 2, isn't it? This went from 4 to 8. That's an increase of 4. You see what's happening now? We don't have enough evidence to prove this, because whenever you have gaps, you don't know how that curve is going to rise. But you sort of get the feeling that this thing is rising far from linearly. That this thing is going to rise steeper and steeper and steeper. Look, I've already used up this whole sheet of paper. But look what happens. Suppose I went 1 more unit. Suppose I went to 4 over here. What's the next height going to be? Every time x increases by 1, the output doubles. Well, when the input was 3, this was the output. When the input's going to be 4, this output here is going to be double this one. Look how high this is going. This thing is going to rise steeper and steeper and steeper. By the way, it does create a problem for us here that we haven't had before. Look, suppose I want to find out, this is 1, this is 2. Suppose I want to find out for what x value this would be, say, 3. So I could come over here, remember what we did? Come back to the curve, and then drop down over here. This would be some number over here. But notice, however, that up until now, the exponent has always been a whole number, or it's been an integer. What do we do with a fractional exponent? See, let's remember now what we have to do. I just want to show you some of the definitions that are forced on us. See, we know that 2 to the 0 is 1. We also know that 2 to the 1 is 2. We also know from that picture that as x increases, so does the output. So if when x is 0, we get 1, and when x is 1, we get 2, when x is a half, we should get something between 1 and 2. The question is, what number should it be? Well, some people argue, gee, shouldn't it be just the average of these two? But let me just flash back here for a second and show you what makes averaging dangerous. See, if you were going from here to here along a straight line, when you went halfway from here to here, you also would have gone halfway from here to here height-wise. But do you notice that this line here is rising steeper and steeper and steeper? Let me see if I can show you a different way. I just want you to see something that I think is very important. I'm going to draw this freehand just in the hopes of saving time. Let's suppose I have a curve that stays very, very, very close to the y-axis and then shoots to the x-axis, then shoots up very rapidly. So in going from here to here, say, okay? Now, look at how big how far the curve has jumped in going, say, from here to here. But suppose I go halfway from here to here. Halfway from here to here brings me over here. I come up to the curve. Is this point here anywhere near halfway between this and this? You see, what would have been halfway is if this was a straight line. But you see, when the graph is not linear, you can't say halfway in this direction is going to bring you halfway in this direction, because it really depends on how the curve is shaped. So going back to where we were before, it might be a nice guess to say, gee, since a half is halfway between 0 and 1, I think the answer here should be halfway between 1 and 2, and you might be tempted to call that 1.5. But let me show you how we're already locked in over here. Didn't we already agree when m and n were integers that b to the mth power times b to the nth power should be b to the m plus n? Well, let's suppose we still want that to be true when m and n are both a half. See, what would happen to this formula if I took 2 to the 1/2 power times 2 to the 1/2 power? See, 2 to the 1/2 times 2 to the 1/2 means what? We're multiplying like bases, so keep the common base and add the exponents. So the common base would be 2. The new exponent would be a half plus a half, which is 1, and 2 to the 1 power is 2. So in other words, if we want this recipe to be true, what is 2 to the 1/2 power? It's the number which when multiplied by itself gives you 2, but that's precisely what we've called the square root of 2 before. And in fact, if you don't believe this, you can do this thing on the calculator, but rather than do it that way, let's pick an easier one. Let's suppose that I wanted to find 4 to the 1/2 power. Now, I just showed you that what? 4 to the 1/2 means the square root of 4, and the square root of 4 comes out to be 2. Suppose you had a calculator with a y to the x key. Enter the 4, press the y to the x key. Now, your calculator probably doesn't have fractions on it, though some of them do, and some of them can have it entered that way. If you prefer, the decimal form of 1/2 is 0.5. So what you do is you enter the 4, press the y to the x key, enter the 0.5, press it, and the answer that will appear is 2. In other words, even if you don't understand where this comes from, on the calculator, 4 to the 1/2 power will come out to be 2. And by the way, it keeps on going like that. For example, suppose I took 2 to the 1/3 power. See, 1/3 plus 1/3 plus 1/3 comes out to be 1. So if I multiply 2 to the 1/3 by 2 to the 1/3 by 2 to the 1/3, according to the rule for exponents that I've already accepted, that should be 2 to the 1st power, which is the same as 2. Therefore, what is 2 to the 1/3 power? That's the number such that you have to multiply it by itself 3 times to get 2. And that number is called the cube root of 2. Okay? In other words, if you took 2 to the 1/3, in other words, if you took 2 and have a cube root key on your calculator and press that key, that will tell you what 2 to the 1/3 power is. In general, if n is any whole number 1 or greater, b to the 1 over n power is simply the nth root of b, the number that has to be multiplied n times to give you b. And then if the exponent is any fraction, the denominator of the exponent tells you what root to extract, while the numerator will tell you what power to raise it to. For example, suppose you took, let's take a fairly easy one over here. Suppose you took 27 to the 2/3 power. 27 to the 2/3 power. The 3 tells you to take the cube root of 27. What number multiplied by itself 3 times gives you 27? Well, that's 3 times 3 times 3. So 3 would be the cube root of 27. Now, what are you going to do to that? You're going to raise that to the 2nd power. So 3 squared would be 9. So if on your calculator you wanted to find 27 to the 2/3 power, you'd enter the 27, press the y to the x key. If you knew how to enter a fraction, you would then enter the 2/3. If you didn't, you could approximate it by what? 0.6666667, wherever the last digit was. Press the equal sign, and the 9 should appear. And that will account for the smooth graph of y equals 2 to the x or 3 to the x or what have you. In other words, with that as a light explanation, see what happens now? Let me show you how you can now verify that this is really the curve. You see, what's happening is this is easy to see for whole number values of x. But suppose x was -1. This would then say what? 2 to the -1 power. Okay? That would say 2 to the -1 power. What does the -1 power mean? It means the reciprocal of the positive power. That's why we learned these things before. This is 1 over 2 to the 1, or 1/2. In other words, when x is -1, the y value will be 1/2. What happens when x is -2? 2 to the -2 is 1 over 2 squared. That's 1/4. So when you come over 2 to the left, the curve goes up by just 1/4, okay? What happens when x is -3? 2 to the negative 3 is the same as 1 over 2 to the third. 2 to the third is 8, so this would be 1/8. And you see what's happening? As x gets bigger and bigger in magnitude, but more and more negative, what happens over here is what? That the curve gets closer and closer to the x-axis and never reaches it. And how do we get these points in here? Well, for example, if this point over here was 1/2, what would this height over here be? If I do this thing right, that would be 2 to the 1/2 power. That would be the square root of 2. On your calculator, so the exact value here would be what? 1/2 comma square root of 2. But if you wanted a numerical approximation, on your calculator, the square root of 2 looks roughly like 1.4142. And what you find is what? You can fill in every one of these points as you move along here. It doesn't matter whether this was a 2 or not. If this was a 3, you'd use exactly the same logic. The only difference is that the curve would rise more rapidly. Like, look what happens over here. Let's just look at the whole number parts. If x is 1, the output is 3. If x is 2, the output is 9. If x is 3, the output is 27. See why? 3 times 3 times 3 is 27. You see what's happening? Every time the input increases by 1 now, the output is being multiplied by 3. You see how fast this is going? And look how fast this comes down to the x-axis for negative values of x. See, when x is negative 1, 3 to the negative 1 is 1 over 3, which is 1/3. And you see what's happening over here is now you have a curve that's doing what? It's rising even faster than before, because now it's not just doubling every time x increases by 1, it's tripling. And if this was 4 or 5 or 6, the growth would be even more fantastic. And a very important base that we use in arithmetic is 10. In other words, let's look at the special function f of x equals 10 to the x, because that's the one that we use for scientific notation. You see, when you raise 10 to a power, a whole number power, all you're going to do is what? Every time you multiply by 10, you tack on a 0. See, what this says is every time x increases by 1, the output is 10 times as much. Not 10 added to it, but 10 times as much. You see what happens here? 10 to the first power is 10. 10 to the second power is 100. By the time you get to 10 to the 10th power, that's already what? 10 billion. Can you see how fast this thing would be growing if you were graphing it? Look at this. When x is 1, y is 10 units high. When x is 2, the y value is already 100 units high. And by the time x is 10, you're going to be 10 billion units high. You're not going to have a piece of paper that measures that way. But see, the nice part is what? This gives you the scientific notation. See, the same thing over here. 10 to the negative 1, 10 to the negative 2, that gives you what? Your 0.1, your 0.01. In other words, if you're looking at 10 to the negative 10, you see that just names this very, very small number over here. But you start to see how this stuff works. And in particular, later on when we look at inverse functions, actually in Algebra 2, when we start looking to see what kind of, see, if 10 to the first power is 10, and 10 to the second power is 100, 10 to what power will give you 18? That introduces a whole new subject called logarithms that we don't study here. But basically, what could we do over here? Rather than go this way, what I could do is compute what? 10 to the x when x is 1.1, 1.2, 1.02, whatever, and I can graph as many points as I want to get the true shape of the curve y equals 10 to the x power. And by the way, sort of in closing over here, what I don't want you to ever do is to confuse 2 to the x with x squared. These are both exponential types of functions, except that what? In this case, the 2 stays the same, but the exponent tells you how many times you're going to multiply the 2. In this case, the exponent stays the same, but the number you're multiplying by itself gets bigger and bigger. Now, watch what happens over here. For a while, it doesn't look too important. Let's take x to be 0, 1, 2, 3, or 4. Then 2 to the x power. See, 2 to the 0 is 1. 0 squared is 0. 2 to the 1 power is 2. 1 to the second power is 1. 2 to the second power is 4. 2 to the second power is 4. Look at that. They're the same over here. Okay? If I put a 3 over here, 2 to the third power is 2 times 2 times 2. That's 8. But 3 to the second power is 9. So now this one is bigger. And if I replace x by 4, another interesting coincidence, 2 to the fourth power. See, 2, 4, 8, 16. 4 to the second power, 4 times 4 is also 16, so they're the same here and here. And it doesn't look too dramatically different down here. But now, look what starts to happen as x gets bigger. Let's look at x now, 5, 6, 7, 8, 9, 10, and then we'll jump to 20. See, another interesting result is that when you've doubled 2 20 times, the result is already bigger than 1,000,000. See, look what starts to happen over here. What's 2 to the 5th power? It's 2 times 2 times 2 times 2 times 2. That's 32. But 5 to the 2nd power is only 25. Already the 2 to the x is getting bigger. 2 to the 6th power. See, as we go down this column, each time we're going to be multiplying by 2 over here. But here, we're not doing the same thing. See, in fact, what's happening over here, the increase here was 11. See that 25 to 36 is 11? Here it's going to be 13. Here it's going to be 15. Here it's going to be 17. These increases are very, very meager compared to this doubling effect. Look at, by the time x is 10, 2 to the 10th power, when you multiply 2 10 times, that result is already over 1,000. But 10 squared is only 100. Look how much bigger 2 to the x is than x squared over here. Again, look at what happens over here. When x is 20, 2 times itself 20 times is over 1,000,000. But 20 to the 2nd power is just 20 times 20, which is 400. And by the way, even if you make this exponent bigger, if the exponent remains fixed and you allow the base to get bigger and bigger, 2 to the x power will still dwarf it. See, let's come all the way down to 10 over here. See, in other words, when x is 10, 2 to the 10th power is 1,000, right? But 10 to the 3rd power is 1,024. 10 to the 3rd power is only 1,000. 2 to the x has already caught x to the 3rd here. X to the 4th is still ahead. See, 10 to the 4th power is 10,000, and 10,000 is more than 1,024. But now come down to where x is 20. This number here, 2 to the x power, has already grown to over 1,000,000. But what's 20 to the 3rd power? 2 to the 3rd power is 8. 10 to the 3rd power is 1,000, so 20 to the 3rd power is only 8,000. Look at how much this dwarfs, not just this one, but this one as well. Okay? And when we come down to the 20 over here, see, 20 to the 4th power, that's 20 times 20 times 20 times 20. That's only 160,000. And that's already small compared to this, and this thing is going to keep doubling every single time. So in other words, the exponential function is an extremely important function. It's almost what you could call the opposite of linear. In fact, it not only outstrips in growth the linear function, but the b to the x function, like 2 to the x, grows faster than x squared, x to the 3rd, x to the 4th. When numbers get very, very large, exponential growth can kill us. And you see, the importance of exponential growth, we might as well get philosophic for the last couple of minutes. The reason that exponential growth is so important is that many things in life happen by that formula. In many cases in life, things change proportional to the amount present. In other words, for example, suppose we talk about the amount of bacteria doubling in a given situation. In other words, if each bacteria produces 2 bacteria in 1 second, if you have 1,000,000 bacteria, aren't they going to produce 2,000,000 because each one is producing 2? So I think we talked about that before. You see, if you have $1 and then you double it, and then you double it again, and then you double it again, by the 20th time you've doubled it, you have what? Over $1,000,000. I think we may have talked about this in the previous lecture, but to me it's important enough that I'd rather say it twice than no time. So rather than check through what we've said before, it's what I called the good luck pyramid. If each person went out and helped 2 people, and each of those 2 people went out and helped 2 people, by the 20th link in the chain, over 1,000,000 people would be helped with nobody having to help more than 2 people. On the other hand, suppose it was a bad thing. Suppose one person with AIDS went out and infected 2 other people, and each of those 2 people infected 2 other people. Now by the 20th link in the chain, over 1,000,000 people have been infected with nobody having to infect more than 2 people. Now you see the danger of something like that? The fail-safe window in society is shrinking. When things happen at exponential growth, by the time you find the handle to cure that problem, it may have grown out of control. From the positive side, if it's a nice thing, by the time you stop it, you may have received fantastic abundance of good deeds. Keep in mind that the math is impartial. that when you take 2 to the x power, as x increases, 2 to the x increases dramatically. But whether that's for good or for bad depends on how we as human beings decide to use it. But at any rate, I did want to show you some more about functions. We're going to be concentrating primarily yet on linear functions and the like. The key point being what? That all of these other functions that we're going to study, no matter how curved they are, as long as they're smooth, we can always do what? Assume that they're linear near any point that we're interested in investigating. But we'll keep on harping on these points more and more as we go along. But for now, let's close, and with my usual admonition, work hard, enjoy, and stay young. See you next time.